This is the video for section 1.7.1, continuity at a point. So the sort of intuitive notion of a continuous function is the following. It's if I have a function like the one I have drawn here that I can draw without lifting my pencil from the paper. So a function that has no jumps or gaps or holes, that's the intuitive notion of a continuous function. But as you should know by now, mathematicians are not satisfied with just an intuitive understanding. We want to have a very precise definition of what it means for a function to be continuous at a point, so there's no ambiguity. So our formal definition is that we will say a function f of x is continuous at x equals a if the following holds. So if the limit as x goes to a of f of x exists, if f of a exists, so in other words, if a is in the domain of f, and most importantly, if those two things are equal. So if the limit as x goes to a of f of x equals f of a, then we say if all three of these things hold simultaneously, we say that our function is continuous at a. So you might ask, well, why do I really need all three criteria? Or do I really need all three criteria? And let's see that indeed we do need them. Let's see what happens if even one of these criterion fail. So the first thing, we could have a function f of x that has a jump at x equal a. And we know that the formal thing that's happening there is that the right-handed limit does not equal the left-handed limit, which means the limit as x goes to a of this function does not exist. So it fails criterion 1. Another thing that could go wrong with respect to a limit existing is we could have sort of this really fast oscillation at a. So our function never settles down at a. And we also know that that means the limit as x goes to a of f of x does not exist. So in either of these two cases, since they fail criterion 1, we would say our function is not continuous at a. Second thing that could go wrong, we could have a function that just has a hole at a. And I certainly have to lift my pencil up from the paper to draw something that has a hole in it. Or I could have something with a vertical asymptote. So again, a is not in the domain of this function f. So in both of those cases, f of a does not exist, and so neither function is continuous at x equals a. And the final thing that could go wrong is indicated in this picture. So I could have a function, f of x, with a hole and then a value of that point put somewhere else on the graph. So notice here, the limit as x goes to a of f of x is 1. So the limit exists. F of a is -2. However, the limit as x goes to a does not equal the function value at a. And notice that on the graph that has the effect of having a hole with the point sort of not where it should be. It's somewhere else on the graph. So again, f is not a continuous function. It's not continuous at a. So if f is continuous at a, that means that in particular both of the left-hand and the right-hand side of this equation exist and that they're equal to each other. So the limit as x goes to a of f of x equals f of a. So kind of what that has the effect of doing, you can kind of think of it this way. It's like we had a hole at every point, and that was sort of telling us some information about the limit, and then we filled in the hole. So sort of continuous functions have their function values sort of where the limit predicts that they should be. So we're filling in any open holes with the actual function value. So let's do a couple of examples. Let's let f of x equals 2x squared plus 5, and I'd like to know, is f of x continuous at 2? So I'm going to check all three criteria. First, does the limit exist? Well, yes, I can calculate it. The limit as x goes to 2 of f of x is 13. What is f of 2? Does it exist? F of 2, again, I can calculate it. It's 13. Hey, those two things are equal. So the limit as x goes to 2 of f of x equals f of 2, which means f is continuous at 2. And a way to sort of confirm that for yourself is to sketch a little graph. This is a parabola facing up, shifted up 5 units. So indeed, that looks like our intuitive notion of a continuous function. Another example. Let's consider a piecewise defined function f of x to be 0 when x is less than or equal to 0, and x plus 1 when x is greater than 0. And I would like to know, is this function continuous at x equals 0? Well, the first thing we want to do is calculate the limit as x goes to 0. So since we have a piecewise defined function, I need to calculate the left-handed and the right-handed limit separately. So the limit as x goes to 0 from the left of f is equal to 0. Whereas the limit as x goes to 0 from the right of f, I use the second most function, so that's the limit as x goes to 0 from the right of x plus 1, which is equal to 1. 0 is not equal to 1, so the limit as x goes to 0 does not exist because the right-handed and the left-handed limit are not equal. So unfortunately, this is not a continuous function. Oh, sorry about that. This is not a continuous function. I transposed somehow. The graph of f looks something like this, and f is not continuous at 0 because there's that little jump there because the limit doesn't even exist at 0.